All right, so gas practice part one, first section is Boyle's law, and of course Boyle's law, P1 V1 equals P2 V2. And so here's our first question. We've got oxygen gas, which occupies a volume of 250 milliliters at 740 millimeters of Hg. So right there, that is my V1, milliliters, it's always a volume, and that's my P1, 740 millimeters of mercury of pressure. What will the volume be? That means we're solving for V2, and then 800 millimeters of pressure, that's my P2. That's my changed conditions. And so when I plug and chug, plug the numbers in the right spot, P1 V1 equals P2 V2, multiply both sides. I'd have to divide by the 800 to solve for X, and watching my sig figs, there's three numbers in each measurement, it's 231 milliliters. So there's my second question. Sample of hydrogen at 1.5 atmospheres has its pressure decreased to 0.5 atmospheres. And when that happens, there's a new volume of 750 milliliters. What was the original volume? So this time we're solving for V1. See if you can set that problem up. Pause the video and see what you get. Well, hopefully you found that when you plug the numbers in the right spot, 1.5x equals 375, divide by 1.5, and we get our 250 milliliter answer. All right, next up we have Charles's law. And Charles's law, again, V1 T2 equals V2 T1. Or, if you prefer, V1 over T1 equals V2 over T2. Either way works, just whatever works best for you. And please don't forget to change our Celsius to Kelvin. So like in the problem, I don't even leave those Celsius temperatures there. I, boom, go and change them to Kelvin. And of course, we remember we add our magical number 273. So here we've got some nitrogen gas. It's got a volume of 250 milliliters at 298 Kelvin. That is V1 and T1. What is the volume going to be? So we're looking for V2 at 368 Kelvin, T2. So again, set it up using this formula or this formula. Just plug the numbers in the right spot. If you use the fractions, the proportion up above, eventually you're going to have to cross multiply anyway, and you should end up at this point. 250 times 368 equals 298x. So I have to divide by 298, and that's how I get my 309 milliliter. Again, pause the video, set up the second one if you haven't done so already, and then check it out. And so this is what it should end up looking like. Again, I changed my kelvins. Negative 50 Celsius plus 273 gives me that 223 Kelvin. That's my T2. This time we're solving for the old volume, V1. So I have to divide by the 223 to get 142 milliliters. All right. Next up, we have Gay-Lussac's law. All right, and again, your choice, but it can also be set up P1 over T1 equals P2 over T2. And again, of course, changing Celsius to Kelvin. So this first question, gas in an aerosol can, our original pressure, P1 is 100 kilopascals, and it's at 300 Kelvin, T1. It's thrown into the fire. Bad idea. It goes up to that temperature, T2. What is the pressure in the can going to become? So we're looking for P2. So again, either way you plug the numbers in, eventually we should get to this point. So we have 100 times the T2, 1200, so we have 120,000 equals 300x, divide by 300, 400 kilopascals is our pressure. And you can see that in the temperature. From 300 to 1200, you multiply by 4. So the pressure goes from 100 to 400. Multiply by 4. Quadruple the temperature, quadruple the pressure. Again, take a moment if you haven't done so yet. Set up the next problem, pause the video, see how you do. And so here we see, this time we're solving for temperature. You still have to change to Kelvin. So we've got air in the tire. P1 is 200 kilopascals. After the trip, the pressure goes up to 223, so that's P2. The temperature started at 300 Kelvin, so what's it going to end up to be? Well, when I solve for x, it's 335 Kelvin. This time I subtract 273, and that's how I got my 62 degrees Celsius. Next up, Dalton. The total pressure in a mixture of gases is simply the sum of all the partial pressures involved in the mixture. So here we have the atmosphere around us. Air has a pressure of 101.3 kilopascals. So that is the total. And that is made up of oxygen and nitrogen and carbon dioxide and other gases. So those 4 are going into the total. And we know 3 of those numbers. So the total of 101.3 is the nitrogen and the carbon dioxide and the others plus whatever oxygen is. So 101.3 equals 80.08 plus x. Subtract 21, or subtract to get the 21.22. So don't forget to subtract here. A lot of people divide since so many of the other laws require dividing. Then we had the pictures. And I still want you to think about this. I'll go over this in class, but this is representing Boyle's law. And so what you want to notice, all the information is given to us in the first picture. In this picture right here, I wanted you to recognize that the volume is cut in half. So if we cut the volume of a container in half, what happens to the pressure? And how would that look visually, because we know that the number of particles causes the pressure. And over here we should notice that the volume is doubled. So if we double the volume, what happens to the pressure? And what would that look like in that drawing? The last picture, this one has to do with Dalton. And so that first, all the information again is given to us. Here we have hydrogen gas, that many particles, that pressure. Next we have water vapor. And it doesn't matter what the gas is, what we're looking at is the number of particles. That tells us a lot about pressure. So focus at that when you're trying to figure out this pressure. And then when you add gases together, then you simply, of course, have to add the pressures. That's what Dalton's law is. All right, hope that helped for the part 1 section, and we'll see you for part 2